This lesson is for FST, Lesson 4.3 on trigonometric identities. There's several identities that students will be given as a handout in class. They do not need to memorize them except for the Pythagorean identity. That one you do need to memorize eventually. Know that the rest of the properties will be provided to you on tests and quizzes, excluding the names. So students need to know how to use them and how to apply them, but they do not need to memorize them. For the Pythagorean identity, the only thing I want to mention here is that when the book writes the Pythagorean identity, they write the square right after the cosine and the sine. Keep in mind that if you were to do this on a calculator, they would not allow you to do cosine squared. You always end up doing cosine theta squared or sine theta squared, but know that that's the same thing as what they've written here in the property itself. Also, I need you to know that the cosine and the sine here are interchangeable. So if you mistakenly write sine theta squared and then cosine theta squared, it'll still work. This is called the Pythagorean identity because it's equal to the number 1, and it resembles the Pythagorean theorem of a squared plus b squared equaling c squared. We'll do an example of this one at the end of the video. For the opposites theorem here, I just want to point out the fact that there are two different types of negatives that are occurring in these problems and moving forward on all the rest of the properties as well. Here we're talking about a negative rotations. We're talking about moving around the circle counterclockwise. Over here for sine, we do have a negative rotation again because that's next to the theta, but we also have a negative sign in front of the sine or cosine or tangent, and all that means is that these two items, these two pieces of this equation are going to be opposites of each other. So this side will be negative while that side will be positive. Or vice versa. If this side ends up being a negative number, then this side will need to be the opposite of it or positive. The opposites theorem does make sense just logically, but the properties themselves can be used as is. If you're looking at, for example, the unit circle, and we're looking at a number like 30 degrees, the cosine there would be a positive value because you are moving to the right to get to that location. So this side would be a positive value in this instance. But if we do a cosine of negative 30, that would be down here at negative 30 degrees or in quadrant 4, and you would still get the same amount or the same value because you'd still go to the right to get to that point the same amount as you would to get to 30. So those two values are going to be equal to each other. If we do the same thing with the sine, meaning the y value at those same two locations, now we're talking about going vertically to get to 30 and negatively to get to negative 30. So the outcome here, one of them would be positive and the other one would be negative. So that is why you'll see here for the sine that these two things are opposite of each other. One's negative while the other is positive. The same is true with tan. If you're doing tangent, typically we talk about that being found by doing sine over cosine. So if you have a sine that's negative and you divide it by a cosine, you're going to get negative divided by positive, which would result in a negative. For the half-turn theorem, notice that they are doing the cosine and the sine, or excuse me, the cosine with degrees, and then they also do it with radians. So know that you can work these theorems in either case. Again, if we're working with 30 degrees as our sample, if I'm at 30 degrees for cosine, the cosine there would be a positive value. If I add 180 onto that, I would be down here at 210. And the cosine there would indeed be negative. So that is why those two statements are opposites of each other. The same is true for sine. The sine in quadrant 1 here, if it was a 30, would be a positive value. If you add 180 onto that, you would end up getting a negative value. The y value in quadrant 3 at 210 would result in a negative number. So the cosine and the sine there are both negative or opposites of each other when you do a half turn. The tangent is going to be not opposite, unlike cosine and sine, because when you're in quadrant 3 for tangent, you'd be doing negative divided by negative, which turns positive. So the cosine and the sine here for the half-turn theorem are opposites, but the tangent, both half-turn and the original, are the same value. For the supplements theorem, notice that in the half-turn we're adding by 180, and in the supplements theorem we are subtracting. Keep in mind that the word supplements theorem comes from the fact that supplementary angles are going to add up to 180. So if I take a 30-degree angle and I take 180 minus that, I'm going to end up at 150, for example. And so if we look at the cosine first, so we're talking about the x value. The x value to get to 30 would be a positive number. The x value to get to its supplement at 150 would be a negative value. So that is indeed why the cosines here are opposites of each other. That is not the case for the sine, the y value. If we do the y value at 30 degrees, that's going to be positive again, but the y value over here at its supplement of 150 would indeed be positive. So notice how there is a lack of a negative sign on the supplements part of this theorem. The tangent's going to be negative because if the cosine's negative and the sine's positive and you divide those, you're going to get a negative result. So it's very important that students remember or take note of the fact that the cosine and the sine for the half turns are opposites, but the tan is the same. For the supplements theorem, the cosine and the tan are opposite, but the sine is the same. The last one we're going to look at here for our properties is the complements theorem. Complementary angles add up to 90. And this is the only theorem that intermixes sine on one side of the equation with cosine on the other. So let's just take a very simple idea here of cosine of 30. If I have the cosine of 30 degrees, this theorem is saying that the sine of its complement, 90 minus 30, is going to be equal in measure. So the cosine of 30 and the sine of 60 should indeed be the same value or the same number. It also works the other way around. So if I start with a sine of 20, for example, the complement to that should be equal to the cosine of that number. So the 20 and the 70 add up to 90. The sine and the cosine then of both of those numbers are going to be equal to each other. So let's go ahead and put these properties into practice with some examples. First example here, just take note of the fact that you are going to evaluate these without a calculator. You'll use your properties. Typically you'll want to figure out which property to use first. So you'll scan the list that you're given and try to figure out which property applies. Once you've identified which property you're going to use, look at the property and decide if your answer will remain positive or change to negative. So that's your job, is to figure out what property to apply and then decide if your answer is going to be positive or negative. So for example, they'll give you a piece of information. In this case, the sine of some rotation is a 0.15. Think about where the sine is a positive value. That's going to occur only in quadrants 1 and 2. So the y value in quadrants 1 and 2 will be positive. Now we're going to talk about rotating the other direction and see what happens to that y value. So again, if I was here at, let's say, 30 degrees, and now I'm down here at negative 30, obviously then those values would have to be opposites of each other. If you also look at the properties present, the properties that are here in this lesson, obviously what's going on here is the opposites theorem, and if we peek back at that for a moment, the opposites theorem does indeed say that the signs need to be opposite of each other. So my answer here is simply going to be negative 0.15. These two have to be opposite of each other, so if this one's a positive, this one has to be a negative. Similarly then for the sine of pi minus theta would go with the supplements theorem. It's just doing it in radians. If we look at the sine property there, those are indeed equal to each other, so I'm going to leave my answer as being simply positive 0.15. And again, the reason is I used the supplements theorem. Second example here is very similar to the one we just did. They give you some information here about the cosine of a number equaling a variable k. Now we're going to try to compare that or contrast that to the supplement. And again, it's a supplement in radians. So if I go back to that theorem that involves the cosine in radians, I can see here that there is a negative sign there, so these two items need to be opposites of each other. So if the cosine was a positive k, then the supplement to that is going to need to be a negative k. So my answer there on finding the cosine of pi minus theta, the answer there is negative k. Go back to the original here of cosine theta equals k. Let's compare that now to the sine of pi over 2 minus theta. The only property, remember, that combines cosine and sine within the same sentence is the complements theorem. It's also the only theorem that has a fraction in it with pi over 2. When you compare those are going to be equal to each other. So if the cosine is equal to k, then the complement is also going to be equal to k. Or you could say positive k here. Third example here is similar to what we just did, only now with a little bit more detail about the numbers. Now we've got 172 as our angle measure. So we know exactly where we are this time. We're not just estimating. We know we're a little bit above the x-axis. And we're at 172. And we know that the y value at that location is a positive number. It's a fairly small number, but that's because we didn't have to go very far vertically to get there. And the y value is what this is indicating. So we need to find another location different from 172 that would have that same value. So we can use a property to figure that out, which ones have signs that are equal. We could also just use some logic here. We went up to get to that value. Where else on the circle would we go up to get to that same value? Clearly that would happen in quadrant 1. So we would need to do the supplement of 172. So we would do 180 minus 172 to find that actual angle measure. So the x value here needs to be 8 degrees. Keep in mind that 8 degrees is your answer, not the sine of 8 degrees. They're simply asking for x, not the sine of x. So make sure you're giving just the value there of 8. So let's quickly peek back at the supplements theorem there just to make sure that we agree. So for the supplements theorem there, it is indeed saying that the sine and the sine of the supplement are indeed equal to each other and there's no negative signs in front. The last example we're going to look at is for Pythagorean identity. The Pythagorean identity questions are a little bit harder for kids to pick up on. That's the type of question that it is. So let me give you some hints on what to look for. They're going to give you a piece of information about either cosine or sine, and then they're going to ask you about the other one, sine or cosine. So again, they're intermixing in the same question the cosine and the sine. Notice here that they're not asking us for a complement, so it's not the complements theorem. That means it has to be a Pythagorean identity question. So remember that the Pythagorean identity says cosine theta squared plus sine theta squared equals 1. What we can do now is replace the cosine of theta with what we know it's equal to. In this case, 3/5. Now be careful here, I've already made an error. The cosine of theta needs to be squared. So make sure you replace what you're substituting it with, and then don't forget to put a square in. Now we're going to go ahead and solve for sine of theta. Pretend that sine of theta is simply your variable, like the variable x. So if we were trying to get x alone, we would want to square both sides, we'd subtract it, and then we would square root. And those are the same steps that we're going to carry out right now to get it equal to the sine of theta. So I'm going to square 3/5. 3 squared is 9. Common mistake there for kids to say 6. Don't do that. 5 squared is 25. Now I need to get the sine of theta alone. So the next thing I'm going to do is subtract 9/25 from both sides. When I do that, I get 1 minus 9/25. I do need to worry about common denominators here. The denominator is clearly a 25, so to turn 1 into a number that's got a 25 on the bottom, I would simply change that 1 into the number 25 over 25. A number divided by itself is going to be equal to 1. I purposely used 25 because that's the denominator that I need. Now when I do subtraction of fractions, remember to only subtract the top number. So I'm going to maneuver up here now. I've got sine of theta squared equals 16 over 25. That was the result of 25 minus 9. The 25's on the bottom just stay. Now to get the square to go away, I would square root both sides. Keep in mind that you can square root the top and the bottom separately. if you need to. Luckily in this case, the square root of the bottom does go ahead and become a whole number. So we end up with sine theta equals 4/5. If that wasn't the case, if we had a number like 26, for example, we'd want to rationalize the denominator by multiplying through by the square root of that on the top and the bottom to get rid of that square root on the bottom of the fraction. That's not our focus for today, but for now I wanted you to see the steps involved with a Pythagorean identity question. Keep in mind too that when you square root, there will be two answers, a positive and a negative. And a lot of the questions will actually hint at that. They'll say give two answers for the sine of theta. One last thing I want to point out here about the Pythagorean identity type questions is that notice that there was a lot of work to be shown on a question like that. When you do these questions on a test or a quiz, they will be worth a significant amount of points because there's so many steps to show. You can anticipate that questions like this, like we did in number 4 here, will probably be worth 4 to 6 points total. In contrast to the questions that we did for problems 1, 2, and 3 here and our examples, these problems will probably be worth only 1 or 2 points. All you've got is a value that you didn't even calculate, and then you have to determine if it's a positive or a negative. So those questions will be worth much less.